What I want to talk about is sort of again like a topic I've been talking quite a bit about, which is graph neural networks. And specifically, I want to talk about them in two contexts. Like one is I want to ask the question, like, do we really need them? There's this really interesting paper that I saw by Horace He and a bunch of other people that basically said like you don't really need GNNs. Like all you need is some form of label propagation and really simple architectures to get these to work. This is interesting because then graphs would be sort of one of the rare exceptions where bigger and deeper models don't seem to be giving you that much better performance. I'm not really sure why that's the case, so I thought we'd analyze the paper and sort of answer that question directly. And the other paper I want to discuss is it's not really a paper; it's more of a like a bunch of lecture notes. And so these are lecture notes by Xavier Bresson, talking about like recent developments in graph neural networks. It's a fairly long survey. It's about like presentation. It's about 80 pages, but it'll sort of give us like a good high level idea of like when you say graph neural networks, like this sort of means like a whole bunch of things. And so let's just like quickly go through like both of these. And so I guess like before we start reading the paper, I just want to show you the like Horace's tweet because I think it does a pretty good job at summarizing some of these ideas. So basically, so the leaderboard they use is the Open Graph Benchmark leaderboard for products. So this is one of the larger data sets, and typically what you're doing is some sort of like node level prediction. And so you'll see here that like, well, the model they ended up using, you can see is about like 10,000 params, whereas the model immediately before it is like 1,400,000. So you have like this like drastic reduction in size with like improvements in accuracy. They're not huge improvements, but they are. It's still improved enough that it's like number one on the leaderboards. And so that's usually a good sign. Like, I mean, like I saw this criticism on Twitter saying something like, well, like, how dare they say this is the best technique or something, or is that really enough for science? And I actually think it is. Like, I mean, if your technique is simpler than competition and it's better, I think that like represents like a net gain. I don't think this isn't considered an incremental improvement. An incremental improvement would be, for example, taking the ideas from this paper, making the params bigger, changing a couple of stuff. Like this is incremental. This is not incremental. Like this is orders of magnitude better. So if anything, this is a breakthrough. So let's just kind of let's kind of go through it. Uh, and what they talk about is this idea of label propagation. And so the reason this becomes important is because you can think of like in a graph, not all of the nodes are going to have labels. And so if you're trying to predict the label of a given node, you're going to do this based on some sort of aggregation based on from your neighbors. And so what's a good way to do this, I guess, would be the next natural question. And so, yeah, so the people behind this work, there's Xian Huang, like I apologize if I'm not pronouncing their names correctly, and then Abe Singh, and then Austin Benson and Horace. And then this was a collaboration between Cornell and Facebook AI. Okay. So I guess like we sort of have like enough background knowledge to go through this. But before I do that, I want to quickly mention that I am starting a newsletter. So this will be different from my usual content. Like I would say my usual content is more like here's how you can do something. Whereas here I want this to be some sort of like higher level and more accessible to more people. And I want to, so the newsletter is going to be called Career Suicide, and I'm going to be basically covering interesting developments in the machine learning space from a news perspective. And so the first article that I'm going to be covering, hopefully it should be out, like if not this week, then next week. And it's going to be about like the great stagnation of machine learning, like why I believe that machine learning has been stagnating, and what are I think some projects or companies that are exceptions to this rule, and again why it's stagnating, some of the poor incentives in academia and industry. So if you're interested, make sure to subscribe. Like it's going to be, I think, a great post, like very entertaining, funny, and informative. So yeah, so without further ado, let's get started. So here, so let's see. So let's zoom in a bit. So they're saying here that graph neural networks are the predominant technique for learning over graphs. That is correct. But there's relatively little understanding over why GNNs are successful in practice and why they are necessary for good performance. And so we show that many standard transductive node classification benchmarks can exceed or match the performance of state-of-the-art GNNs by combining shallow models that ignore the graph structures with two simple post-processing steps that exploit correlation of the label structure, an error correlation that spreads residual errors in training data to correct errors in test data, and a prediction correlation that smooths the prediction of the test data. All right, so there's a there's a few important ideas here. So the first one is generally like when it like even though a GNN seems like it's this sort of complicated structure, it is at the end of the day still doing something like a matrix multiplication. Um, but and this idea of a transductive node classification benchmark, like this is just a fancy way of saying like you can figure out a given label based on its neighboring labels. And say so I guess like they do this by spreading what they call the residual errors in training data to correct errors. Like I'm not really sure what these statements mean, but I guess like it'll be clear once we go through the paper. And then they call this procedure the correct and smooth, and the post-processing steps are implemented via simple modifications to standard label propagation techniques from early graph-based semi-supervised learning methods. So our approach exceeds or nearly matches the performance of state-of-the-art GNNs, and for instance, we exceed the best-known GNN performance on the OGB dataset with 137 times fewer parameters and greater than 100 times less training time. This is a big deal. Like, so we also incorporate our results, and they just have the benchmarks and they have the code ready. Interesting. Uh, so here's so there's one thing I think I may have covered this in an earlier stream, but let me just sort of mention it. So what was sort of interesting about GNNs, and so there's a plot about this in the so there's a plot about this in the like in the graph convolutional neural network paper. So the plot sort of looks something like this. Basically, you have a number of layers, and then you have accuracy, and then it sort of looks like this. Or maybe it actually sort of looks like this. So basically, let's say here, like at 3, it's great, but then like let's say at 5, it starts to degrade drastically, and then 1 isn't all that good. Uh, maybe like you don't think this is weird. For me, this was extremely weird because it's just really the only field in machine learning where I found this is the case. Like when you think of stuff like ResNet, it has like 50 layers. When you think of transformers, like it's a meme, just make them as deep as possible. So for me, this was an interesting counterexample to this. And if you sort of combine this with a bunch of other results, like basically, there's this recent Medium post that I read, which basically said that GNNs are basically so transformers are GNNs with attention as the neighborhood function. So this sort of tells us that GNNs is sort of like this powerful, all-encompassing framework. And the fact that transformers fit in this framework, and that also GNNs are outperformed by label propagation. So basically, this paper. So for me, this is sort of an indicative that maybe simpler models are actually better, right? And so this, if this should be very surprising, if you're used to deep learning, because generally this is not true anecdotally. So let's just sort of see like what they did and sort of how they built the argument. All right, so following the success of neural networks in computer vision, natural language processing, there's a wide range of graph neural networks. So we're going to be covering a lot of these in the survey, so don't worry if these don't make sense. But the main point is that there's a whole lot. They basically differ in either their aggregation function or their pooling function. Um, and then the main benchmark is the open graph benchmark. So often methodological developments create like better architectures, such as you have graph attention networks, graph isomorphism networks, and various deep models. And then many of the ideas are yes, okay. So basically what this is saying here is that like, well, like we had transformers and CNNs work really well in their domain. So like, why wouldn't we incorporate their ideas into graphs? It's a sort of very natural idea, but here they're saying, well, actually, we realized with simpler models we don't need this. So what they say is we propose a simple pipeline with three main parts: a base prediction made with node features that ignores the graph structure, a correction step which propagates uncertainty from the training data across the graph to correct the base prediction, and a smoothing of the predictions over the graphs. So steps 2 and 3 are just post-processing and use classical methods for graph-based supervised learning, namely label propagation, with a few modifications, and we achieve state-of-the-art performance. Okay, so let's look at this. So overview of our GNN free model. So correct and smooth with the toy example. The left cluster belongs to orange and the right cluster belongs to blue. We use MLPs. Oh, I see. So you have these input features, and then so how does this work exactly? So why is this a bipartite graph exactly? The graph structure is not used to learn parameters, but instead as a post-processing mechanism. We also combine our ideas with state-of-the-art GNNs and see. Okay, sure, this is like they just boost a bunch of stuff and get better results. That's fine and that's fine and all. Oh, I see. So label propagation, it's interesting, was used in 3D, right? So in point cloud data, there is a direct relationship between all points, as in the distance among them, like let's say the Euclidean distance among them. And so like, given a new point, it's actually fairly easy to figure out its distance to everyone else. Because you can use basically the triangle inequality and sort of very, very quickly compute the distance to everyone else. Think of it like a KDD tree or something like that. It's basically just like a data structure where if you add a new point, you can very quickly figure out like how it's supposed to be clustered. So recent research connects GNNs to label propagation as well as Markov random fields, and some techniques use as hoc label information. Okay, so I still don't quite understand this. So they're saying we have these input features and we have these training labels. All right, and then we have an MLP that does the base model predictions, and then yeah, I'm not really sure I follow any of this chart. For error correction and smooth, these post-processing steps are based on the fact that errors and labels are connected and nodes are positively correlated. Let me just mute my phone. Okay. So overall, our methodology demonstrates that combining several simple ideas yields excellent performance with a fraction of the cost. On the OGB product benchmark, we outperform. Okay. Okay, I think let's just go to the notation because this is, let's see, what is the algorithm? Okay, so it's just 2 pages and then the rest is experiments. So we already sort of know that the experiments are good. So let's just, I would say, dive straight into the core algorithm to see how it works. All right. So we assume that we have an undirected graph where there is v nodes with features on each node represented by n times p, right? So let's assume that each node has basically p features, for example. And so it would be something like this. And then you have an adjacency matrix, which is a, right? And it's going to be n times n. And then you have the normalized adjacency matrix, which is d half a d minus half. So what this is like, they call this like the normalized adjacency matrix, and this is motivated from spectral graph theory. But basically, the degree matrix tells you given a certain position, it tells you for that node to how many other nodes is it connected to. So it gives you like a sense of how many outgoing edges are stem from that XY position. Um, yeah, and it's a diagonal matrix, because for each point, because you only need to figure, like, basically you have endpoints, right? And so on the diagonal, you're also gonna have n elements in this case if it's a square matrix, right? Um, so for the prediction problem, the node set is split into a disjoint set of unlabeled nodes and labeled nodes, which are subsets of the indices, right? So because there's n nodes, and we represent the labels as a one-hot encoding, where there's, like, let's say C classes. And we further split the labeled nodes into a training set and a validation set. Our problem is transductive node classification. Given each node J and U a label, given assign each node a label given G, X, and Y. Yeah. So basically, given so what was G again? Validation node. Okay. Yeah. So given the graph, the node features, and the node labels, figure out the missing ones, right? So what they say is, okay, well, we our approach starts with a simple base predictor on node features, so which does not rely on any learning over the graph. So we perform two types of label propagation: one that corrects the base predictions by modeling correlated error, and one that smooths the final prediction by modeling correlated. Okay, I don't know what any of this means. We call the combination of these two methods correct and smooth, and the LPs are used as post-processing steps. This makes training fast and scalable. Okay, great. Yeah, so they've explained this already. This is uh, not new. So okay, I guess the algorithm starts here. So we use a simple base predictor that does not rely on the graph structure. So more specifically, we train a model F to minimize this, where xi is the ith row of x, and yi is the ith row of y, and L is a loss function. Ith row of x is the ith row of y. Oh, I see. Yeah. So given all of a node's features uh and given a node's labels, because the ith row of y is going to be uh, so I guess here, like, how are they saying yi? So oh, I guess, like, there could be also by one hot encoding n times c is the number of classes. Yeah. So each row is going to be like a single value in this case, right? Uh, and so Okay, so we basically learn this, like, MLP. So it's either a linear model or a shallow multi-layer perceptron followed by a softmax. And then we get the base prediction where each row we use a new base prediction. Okay, so I would say, like, let's just simplify this a bit. Basically, step one is MLP from node features to node label, right? So this is typical supervised learning. So the next step, they're saying, well, we're going to correct for error in the base predictions with residual propagation. So we improve the accuracy of the base prediction by incorporating labels to correlate errors. The key idea is that we expect errors in the base prediction to be positively correlated along edges in the graph. In other words, an error at node I increases the chance of a similar error occurring at neighbors of. Okay, so we should spread such uncertainty over the graph. Our approach here is inspired in part by residual propagation, where a similar concept is used for node regression tasks. Okay, so we define an error matrix, n times c, where c is a residual error on the training data and zero elsewhere. So, oh, I see. So it's a residual error per node per label, right? Remember, so n is number of nodes, and then c is number of labels. All right, so we basically take this residual error, and so what's z? So we improve the accuracy of the base prediction z. Okay, yeah, so the base prediction zlt minus ylt. Okay, interesting. And then what's e of lv? So we use smooth error using the label spreading technique of Zhu et al. optimizing the objective. So we have WI, and so what's S? Okay, so here, this feels like some sort of regularization, right? It's taking the Frobenius norm between the weight matrix and your residual errors, right? And then here it's saying the equivalent of I minus SW squared. So what's S again? I can't. S. Oh, the normalized adjacency matrix, right? Okay. So we minimize the trace of the normalized adjacency matrix times W plus this is the smoothing. And so S is the normalized adjacency. So I guess we really just need to read this paper to figure out why this works. But they're basically saying, okay, well, the first term encourages smoothness of the error estimation over the graph and is equal to this, where Wj is the jth column of W. And the second term keeps the solution close to the initial guess E of the error. So we know that in general, the E at the time step, okay, so we can use the fusion like the one from Zhu and Al, which keeps the known errors at training nodes fixed. Okay. I think homophily is like liking people that are similar than you. Let me make sure. Yeah, okay. By another label propagation, we start with our best guess of the labels, Y, and then we set the training nodes back to their true labels and use the corrected predictions for the validation. We then iterate this until convergence to give the final prediction. And then the classification for the node is the argmax. Okay. Yeah, I think I'm getting some high level sense. So they start with a basically, so this is the cheap MLP prediction. And then basically, you know what the true label is, right? So you can look at the error that your MLP has over the known nodes. Like basically right? Not like the unknown labels, like the known labels, like you would mask them out. And then once you get those errors, you correct uh like yeah, so let's do basically local features and then get error, then correct neighbors, um, and then smooth neighbors. All right, so yeah, so I guess they say that it's just like three steps of the pipeline. So this, I guess, just like I guess part of correct neighbors, but whatever. Um, so we then iterate this until convergence to get the final prediction. We set the training nodes back to their true labels and use the corrected predictions for the validation on label nodes. I see, interesting. Yeah, so I guess the best guess is always going to be this residual error. And then, let's see here. Simple base predictor, correcting the error. Okay, so to review our pipeline, we start with the cheap base prediction. All right. After we estimate errors by propagating known errors on the training data, uh, we estimate errors E by propagating known errors on the training data, resulting in error-corrected predictions. Sure. And finally, we treat these error-corrected predictions as score vectors on unlabeled nodes, or combine them with the known labels through another uh, label propagation step to produce smooth final predictions. Oh, I see, I see. So I should this is not very accurate, I think, or it's like sloppy a bit. So basically, you get local features, right? This gets you an error. Then use neighbors to correct errors, like known neighbors. So I mean, yeah, like this is sort of a it's a fairly, I think, straightforward approach at this point. So let's look at this. I mean, just the parameter count drop is just absolutely staggering. I think this is like for me, this is the biggest deal. Like this is just straight up nuts. This is like you like this is orders of magnitude, right? Like when people even get 20% or 30%, they start jumping up and down. But the fact that they can like go down like over about 100% and parameter size is a big deal. The accuracy improvements are incremental, but then like if you see this, like for the larger products, it starts to matter. Like this is 2 billion nodes. But imagine like something like a healthcare data set, right? So this could be hundreds of billions of nodes. So this differential is really going to matter a lot more. What's cool is that they also have their code. So let's just check this out. Let's check out the code next. Um, GitHub. All right, let's check this out. Just sort of get some sense of how complicated is this code base really. So I get phone it. And just give this a minute. Has some Julia code. Interesting. Oh, I see it. Yeah. So this. I mean, yeah, you see. So this is the normalized Laplacian code. Like it sounds complicated, but at the end of the day, like you're really just using a bunch of linear algebra libraries. Okay, this looks like some sort of archive linear value pi array. All right, whatever. So let's see. So the diffusion features. Okay, so this is them, I guess, comparing it to graph attention networks. Let's kind of skim this quickly. Yeah, you can see here, like the model is fairly trivial, right? It's just like an MLP, and then there's like a linear MLP, like batch norm. Okay, like absolutely nothing crazy going on here. Testing with the evaluator. It's interesting how they use the Julia. Like it's not something I expected. It's just here, like they'll say, okay, from Julia API import Julia, and then Julia compiled modules. I don't know, is this easier to call Julia code from Python? I may end up doing it more often. I see, so you just say main.include norm spec, and then two undirected. Let's look at norm spec again. Okay, so this is where the main function is coming from, it looks like. Okay, very cool. So I'll take a closer look because I do want to end up running this. And I guess like wait, I think they made it pretty. I'll do this. I think they made it pretty easy to try different data sets. Like let's see, uh, valuation. Oh yeah, run experiments. Oh yes, okay. So they're just using the Open Graph Benchmark data loader, and then it's just as simple as pulling it in here, and then they can process the adjacency matrix here, and then they have this evaluator. All right, so here they set it up as a sparse tensor and degree inverse square root. Yeah, so here they're doing like this is so that they can do the like this is the d minus half part, so you can get the normalized adjacency matrix, right? Yeah, so this is it here. The d is square root. Apologies. All right, I guess it's time. Let's go to the survey now. So I was saying this earlier, but this is a survey by Xavier Bresson, and I think I saw like Jan LeCun retweet it, and so it looked kind of interesting to me. So let's just kind of I guess like slowly go through it and see what's going on here. Okay, so the first thing they're talking about is the Weisfelder Lee Man GNNs. So this is important basically for like graph isomorphism. And this is important. I have another stream about it to show basically like to compare power of GNNs, right? And so there's like, here I see they talk about it explicitly here and here. Okay, and then we're gonna talk about graph positional embeddings. Okay, yeah, so we're not really looks like talking about like explicitly stuff like graph convolutional neural networks or something like this. Looks like it's a bit higher level. Let's just get started. So two graphs are isomorphic if there exists an index permutation between the nodes that preserves node adjacencies. So, oh yeah, sure. Because here you see here H, O, and F. H, O, F, and C, right? Like they create like this path. So instead of it looking like this, you could make it look like this. And so really this is trying to say if you just like basically change the labels or change the shape of the graph, like that you can get one from the other. And it looks like this is sort of a hard problem, but it's not clear how hard it is. There is no proof to say whether it's NP complete or not. And the test to figure out if two graphs are isomorphic is not guaranteed, and I believe because it's a randomized or not random, it's a probabilistic algorithm. Like basically, if you run it, you're pretty sure that two graphs are not isomorphic, but you may not be really sure if it is indeed isomorphic. Typically, these tests work on, like sort of like you're sampling elements from the graph and then running a test. So that's why you end up with this sort of argument. So the idea is you design an injective coding function that takes a pair of nodes as input and outputs a new color, and a unique color for the same pair node, its neighborhood. Uh, sure, yeah. Different colors for different pairs of nodes. Okay, simply said, must be an injective mapping. Injectivity is a discriminative property that takes a pair, node, and its neighborhood as input and outputs a new node color. Okay. Uh, I think terminology there is a bit complicated. Let's come here. So the algorithm iteratively applies the coloring function until no new colors are created. So let's say at step one here, looks like, how are these colors? Okay, you have a bunch of colors here. Okay, this doesn't explain anything. If the two graphs have different color histograms, then they're guaranteed to be non-isomorphic. Okay, like this is making a bit more sense. So basically, almost think of it like a sort of like a hash. Let me do black, be clear. So if you take a hash of graph 1 where the output is a histogram, uh, basically it shouldn't be equal to histogram 2 of the hash of graph 2, if they're not equal. Yo, hey pseudomaze, how's it going? Thanks for joining. Yeah, it's all about GNNs now. Like I guess like goodbye transformers, now it's all about graphs. All right. So I guess like how the test works, I don't think is the interesting part. I think it's more that it can create like a hash, and so I think that's sort of the main idea. So can we turn the WL test into neural networks to classify non-isomorphic graphs? Yes, but it is necessary to have a learning process for WL test. No, but designing constraint free is hard and easier to do in a learning setting. Distinguishing non-isomorphic graphs is not necessarily useful in practice, as the coloring process that can provide a rich representation of data structured graphs and can be used for downstream tasks like graph classification or regression. Oh, I see. So they're basically saying that uh, the stream lags for a bit. Oh, that sucks. I'm not sure actually, because I think internet has been bad all over now. Like since honestly, since elections started, I feel internet's been awful. It's like that if the world's starting. Okay, so the test iterates the coloring formula. So for each node and its neighborhood, it provides a unique color for the same pairs and different colors for distinct pairs. This implies that the function must be injective. So which functions are injective? The max is injective. I see. So yeah, so it basically means you can figure out my fix. Oh wow, okay, that bad. Uh, hmm. Oh yeah, it's saying drop frames detected 26%. Let me lower my bitrate maybe. Yeah, it was mostly like, yeah, it's like here, Twitch was set to auto. Okay, let me know again if it causes any issues. So this is interesting basically. So let's say you're trying to aggregate like a bunch of inputs. If you do the max operation, you can figure out. Oh, yeah, I have it set to. Oh, I see. Okay, interesting. So if you do the max operation, you can figure out which element was the max, right? But if you do a sum or a mean, then that doesn't discriminate like a single node. Okay, and so then they're saying, can we create a neural network such that it takes the current node and then all of the nodes in the neighborhood? Uh, so the sum aggregator, mean and max are not injective, where it must have. Here. So remember, basically, we're saying for uh, like again, remember the coloring analogy, right? So for each node in the graph, we're trying to figure out the correct color, and then we do this based on like basically f of this is equal to basically the sorry like the features like let's it's going to be xi if this is like x of sorry this plus sum of x of the neighbors of this, right? So this is sort of the general structure. Like this is the current node, and then this is your neighbors, and you sort of weigh. how important each one is. So the graph readout aggregation must also be injective. So, okay. Cumulative power can learn different graph representation. Okay. Yeah, so this was in the graph isomorphism paper. Like these are screenshots. I've covered this paper on stream before. Um, but basically here, like what they say is like they pick different graphs, right? And different aggregators. And then they're saying like, can we distinguish these two graphs using the mean or max or whatever operation? Um, so here the aggregators that fail here, for example, it's the mean, and here it's the everything except the mean. And then what is this equation here? So it's saying the value of the node at the L plus one at uh, at layer L plus one is equal to the features of this node, and then the neighborhood times the weights. Oh, I see. Okay. So basically, as opposed to just having like an aggregated sum, like you have an MLP that learns this, and that's where this W comes from. So graphs are rank 2 tensors, and they can be represented like this. And then vectors are rank 1 tensors, all right. Is the invariance of the topology index permutation. So what's going on here? We're just flipping the columns, it looks like. But how are we flipping this exactly? Oh, okay, yeah, we're just, oh, Jax is really dope library. I'm using it for my convex optimization project for my final project. Yeah, like I have some friends that use it at work. I haven't done a Jax tutorial, but that would be interesting. Was there something you liked about it over something like PyTorch, for example? Like what did you feel was the main difference? I guess like speed is one aspect, but also like your productivity. Do you feel like you can do more with it? Let me go here. All right. Equivariant functions, invariant functions, or readout layers. It's just a better NumPy, and PyTorch has its own setup for deep learning stuff. Well, that's interesting. So I guess like most libraries haven't really been developed in it either, from the sounds of it. On the differential stuff, yeah, I see. So it's more like a Julia and Python then it sounds like, right? Great inductive biases, less parameters to learn, faster training, yeah. So yeah, so this was interesting. I keep seeing like this is not the first time I see a slide like this, but I think it's really cool. Like the fact that the order in which you apply the operations doesn't matter. So this is just like a form of symmetry. And so an MLP is a composition of linear functions plus nonlinear activations. Oh, linear layers. Oh, I see. I like this notation a lot actually, because I've been used to basically saying like basically drawing it like this. and then ReLU. So it's like it's all matrix multiplication argument. So I say this is like nice notation. I'll be borrowing this, I think. So equivariant GNNs, um, composition of equivariant linear functions plus nonlinear activation ReLU plus invariant linear function plus final layer function for classification regression. So we have equivariant layer and then final input layer function, equivariant linear function, invariant layer. I'm still confused on what they mean by equivariant and yeah, so they're saying there are two types of equivariant functions are defined as functions where if you say you do this and then this, okay, so the order doesn't matter with equivariant functions. Okay, so this is order doesn't matter. And then where was this? Here, equivariant. And then I guess the label name doesn't matter. So given a rank 2 tensor, can we fully characterize all equivariant invariant linear functions? What is the biggest collection of invariant layer? Okay, the space of all equivariant linear functions fully characterizable and of dimension bell of 4. What's bell? Invariant. Oh, it's like I see invariant and equivariant graph networks. Yeah, I figured this would be a theory paper. It's hardly any experiment. I think I need to read this. Equivariant, invariant. Yes. All right, maybe we can linear and invariant functions. Okay. So the 15 equivariant linear functions are defined as the identity and transpose, the diag operation, sum of rows, sum of columns. Okay, and then so this is the near equivariance. From one dimension input to one dimensional output. Okay. Oh, interesting. I see. PWO. Oh, I see. Okay. So basically, instead of just looking at neighbors, look at look at sets of neighbors to do the coloring. Okay. And so then start like the. Okay, this is interesting. So we're basically saying here, so these are some features. So GNNs can't detect cycles or clicks in general, um, at least with the message passing GNNs. I see. So it's like really this is sort of, I guess, where you want to be after this. It becomes like a bit too slow. So any continuous function invariant by permutation. So which papers do they use here? Theorem 3. On the universal. So this is like Maron Fataya. These guys seem to show up quite a bit. Any continuous function invariant by permutation can be arbitrarily approximated with the necessary condition that the network has a tensor of order a polynomial of n, where n is the number of nodes. I see. Okay, so here, for example, we can say can include physics. Okay, so basically here, for example, they're saying as opposed to doing a general classification, basically, can you, like, which combinatorial uh, problems can you solve with GNNs, right? And so basically, looks like almost none of them, right? So they failed to propagate long distance information, causing overfitting and poor generalization. Uh, on the bottleneck of graph neural networks. Okay. A fully connected graph layer, every pair of nodes is connected by an edge. Complexity is big O n square. It improves performance without any hyperparameter. Oh, I see. So we can basically also add uh like positional encodings, like in BERT, position encodings, because like the meaning of like basically or the impact of a feature uh also depends on its place in the node. So this is sort of like combining ideas from transformers as well. Um, Arbitrary orderings to the node. Possible sign flips is k being the number of eigenvectors. In practice, we choose k less than n, and therefore okay. I mean, yeah, sure. Basically, here we're saying, where was it? Yeah, so either the encoding depends on your immediate position, or it depends on your position and your neighbors, or it depends on some sort of cyclical property as well. There's like, think of it like a hash map that's circular, for example, like prediction task. All right. I think that's gonna be it for me. Like, so I think what was interesting, sort of to cover the basics of what we talked about today. So I think it's like it's a very dense. This is a very dense talk, by the way. But sort of like what it's trying to do is it's sort of taking the original graph isomorphism complexity paper that basically said like, look, there's this thing called graph isomorphism. Most GNNs are weaker than that. So here we propose an algorithm that's better. And here it sort of studies it more from a complexity theory perspective, and it looks at the expressivity and the complexity of each of the different graph neural networks architectures, and gives a framework for what future graph neural networks look like if you just made them more expressive and complex. The interesting thing about graph neural networks is that they're sort of a composition of these invariant and equivariant layers, where one is your label doesn't like your name doesn't matter, and the other is the order in which you apply features doesn't matter, similar to in convolutional neural networks. Uh, and we use this as a framework to sort of figure out like, well, what kinds of problems are theoretically solvable with GNNs using this framework. Turns out most interesting graph problems aren't solved by GNNs. Like you can't solve combinatorial problems on graphs with GNNs. Uh, and then finally, the last thing they talk about is how to use features that also depend on your position. So similar to how in BERT, like we have positional embeddings in words, like where let's say we want to have n squared, and we want to make sure like, well, this is coming before, this is coming after in a graph. Let's say in the case of dynamic graphs, this would be very relevant, right? So you can have these sorts of features, and either they can be inspired by your just immediate position, or on the local structure, or it's something like a bit more cyclical. And the other paper we discussed is like this sort of seems like just like a very a complicated way to think about GNNs, but what makes me optimistic was the earlier paper by so WL is this test. So it's this here. It's the Weisfelder Lee Man Test. And basically, it's a probabilistic test that lets you figure out whether two graphs are isomorphic. The idea is that if a GNN can't tell that two graphs are different, it's probably not a very good GNN. And it turns out like the basic one, like graph convolutional neural networks, just can't distinguish most graphs. Uh, so here, like this whole survey is really about like what can you distinguish, what can you study, what is the actual power of GNS. So it's like a very theory heavy paper. So there's a couple of background papers that I feel like I want to read next. But there's a big but. With this paper, it makes me a bit optimistic because I think this sort of made my head hurt a bit. Like this was sort of a, I feel like I need to just spend like the entire day just slowly reading this because it was very dense. This paper, on the other hand, covers a very simple algorithm, and basically, instead of doing GNNs, it proposes that you can just basically ignore the graph structure, do some sort of supervised learning problem on an individual node, and then basically propagate the error to your neighbors because you know what the true label is. And so this sort of really simple label propagation algorithm with very tiny models that are 100 times smaller than the state of the art in GNNs actually outperforms them. Not by much, but at 100 times less parameters, it is a big deal that you still outperform them. So it's actually not clear to me. Like I'd say with GNNs, I still think the jury is out. Like, are these techniques actually useful? Like, or is it like sort of interesting from a mathematical perspective? I think the jury is still out, but this paper, at the very least, I think really challenges my optimism with GNNs because it sort of tells me that maybe all you need is something simple like label propagation, and generally simpler methods are more likely to be correct just by the Occam's razor heuristic. So yeah, I mean, I hope this was informative. I think I'm gonna go grab some tea and just to search, look at political news on Twitter. I did want to say that I did start a newsletter. So if you go to Mark Seraphim at Substack, I want to be covering more machine learning news. So this is not going to be as technical as my usual content, but it's going to be more talking about societal uh, or social problems in ML. And so my first paper is going to be on basically what I consider to be like the great stagnation of machine learning, like why I feel the field is stagnating, like the incentives, uh, who is doing a good job to avoid these problems. And so I was supposed to publish it today, but then I got distracted with the news. So let's see. Hopefully it'll be out like either end of this week or next week. So I hope this was fun. If you have any other suggestions for topics, like please feel free to let me know. And I'm just gonna go grab some tea right now and chill. So thank you so much, especially Mazen. I really appreciate it.